let's talk about GLIMMIX in general before we get into some specifics. Again, GLIMMIX is this SAS procedure that lets you deal with nonlinear models, but it also lets you deal with linear models. You know, you can use GLIMMIX to analyze the FEV data set if you want to. Even though MIXT was set up to deal with linear models exclusively, GLIMMIX could be used for linear models. Its primary purpose was to deal with nonlinear models. And one of the key things about GLIMMIX, and again, let's see if I get this thing up on the screen larger, is that when you're dealing with GLIMMIX, you can have fixed effects and random effects. And we previously talked about GenMod, which allowed you to also deal with a nonlinear model. But GenMod didn't allow random effects. So GLIMMIX is more general, and that's why people are tending to use GLIMMIX almost any time you have a nonlinear model, or even a linear model, as SAS recently wrote that they recommend that you use GLIMMIX for everything, pretty much, if you're using SAS procedures to deal with correlated data. So that's one thing. And the GLIMMIX model is a little tricky compared to the general form of the GLIMMIX model is a little tricky compared to the form that's the model for the linear model for ProcMix, because you've got the random effects come in when you're conditioning on random effect, when you're conditioning on the expected value, and which relates to the link function and how it works. So it's a little tricky, and the main way that it's tricky, the main way that the problem comes out is that formula for the variance covariance matrix that worked for the linear model, the ZG, Z prime plus R formula, doesn't work for GLIMMIX because it's a nonlinear model. So but it's okay, because when you're dealing with GLIMMIX, there is this a code procedure that you could type in VCAR, and the computer will work with whatever the correct formula is. It will work with that and not worry about the fact that it's ZG. It's not ZG, Z prime plus R, and you'll get the appropriate or the correct estimate of the covariance matrix, even though there's not a neat formula for it. So who cares that there's no neat formula as long as we can get it? So that's one thing. But the other key thing about GLIMMIX compared to MIXT is that when you're using GLIMMIX, you have to write all the decisions about what the R and the G matrix are in terms of random statements. So you have to write two random statements, one random statement to indicate to what extent you want an R matrix or what the R matrix is, and a different random statement to indicate what the G matrix is, what the random effects are. With MIXT, there was a repeated statement and a random statement. So you just have to get used to doing that. And in the random statement, with the two random statements, when you want to use an R matrix, you have to type random residual. The key thing is random, the key word is residual. When you write random residual, that's telling GLIMMIX that you're putting in an R matrix, or you're dealing with an R matrix. Okay, you got that? So random residual. Now, one thing in the code, when I showed you some code at some point, when I wrote this code and showed you this, I'm going through this fairly quickly, but you see where it says random underscore residual underscore, and then it's got subject equal ID, type equal to CS. That's the correlation structure that's being used. But you see the underscore residual underscore. Toshihiro came up to me and asked me, do you really need this underscore business? Could you just write it random residual without the underscore? And the answer is yes. You don't, I don't know why they wrote it like that originally in the user's guide, but if you just write random space residual, and then I don't even know if you need a space, and then a slash, you're okay. You'll be able to get an R structure. So this particular code allows you to tells the program to fit a model. In this case, it's just an example of it's a test example, but it's a model where there's an R matrix that's compound symmetric or exchangeable, and there's a G matrix which is a scalar. It's a 1-by-1 scalar because there's only a random intercept. There's not a random slope in there. Another key thing about, I just want to kind of review to some extent about the GLIMMIX procedure is that in order to run the procedure, you have to tell it what method it's using. And the method that GLIMMIX is using is not exactly the same method that's, it's a GEE approach. It's a way of getting solution to what are called quasi-likelihood equations, but the quasi-likelihood equations that are used for GLIMMIX are not the same as the quasi-likelihood equation used for GenMod. And in fact, the method involves some kind of an approximation. You may remember my writing showing you this horrible slide, which on this slide, on the top part of the slide is the formula for what it's worth for these quasi-likelihood or GEE equations that's used with GenMod, and underneath it is the formula that's used for the GEE equations that the computer uses to solve it for GLIMMIX. And the key thing about what's on the screen is that they are two different formulas. So the method used for GLIMMIX for getting these estimates isn't exactly the same, and the method in fact involves something where it involves a linear approximation to the outcome variable, and that's why in this expression over here I have a y star, which amounts to when the computer is running GLIMMIX, what it does is it transforms the outcome variable, actually transforms the model from a nonlinear model to a linear model, and transforms the outcome variable and the other variables in the model in order to actually run it as a linear model. And as a result of that, because it actually changes the nonlinear model to a linear model, it actually then proceeds to come up with answers using the same rules, the maximum likelihood rules that were used to solve Proc-mixed equations. And so you wind up getting, when you're using GLIMMIX, you wind up getting F-tests and T-tests, which is what you get with Proc-mix, as opposed to chi-square tests that you get with GenMod. So, and more important than that, in terms of that's a little worrisome when you think about what GLIMMIX does. It's using a transformation. So it's not using the original data to come up with the estimates. It's using some kind of approximation of the original data, and they're sometimes referred to as pseudo data. But it's not completely pseudo data. It's not made up data. It's a way of transforming the original data to something that is going to allow you to get a reasonable answer. But the thing that worried me when I first saw this was that, well, if it's using a transformation and it's getting an approximation, if I have the same situation that I might want to use GenMod for, where I have no random effects. GenMod I could use for a marginal model, and I have GLIMMIX and I have a marginal model and want to use GLIMMIX for it, will I get the same answers? In other words, if one of the methods is giving me an approximation, the other one isn't, will I get the same answers if I have a nonlinear model? And essentially, what I've read and in the literature on this is that more or less you're essentially going to get the same answers. So it's probably not worth worrying about the fact that GLIMMIX is an approximation. It's an approximation that has to do with what's called Taylor series approximation. Apparently, it's a good approximation. So I don't think there's worry to be concerned about the fact, but I was worried about when I first saw this thing. So what I'm essentially saying is, if you might think this is a cause for not using GLIMMIX, it's not. I mean, GLIMMIX has now been used as a procedure for a number of years, and it's been shown to be fine. So don't worry about that approximation. But the approximation does do some limiting. It has some limiting things. For example, and I have it somewhere over here. Well, let's see. Now I had some examples. I'm trying to find where this relates to. Where am I going with this? Oh, yeah, okay. If you want to test a hypothesis, let's say, for example, you have a logistic model, it involves, maybe it's even a marginal model. A marginal model, and it's a logistic model, and you have correlated data. And the model has main effects and interaction terms. So you have an exposure variable, you have variables you want to control for, and then you have some product terms, exposure times some of the variables you're controlling for. And you want to test, you want to do a chunk test, say, for the interaction terms, just like we did in 740. How would you do that test in 740? Based on what we talked about in EPI 740. If you were using logistic regression and you're using proc logistic and you were going to do a chunk test for interaction, what you do is you'd fit two models, right? You'd fit one model, which was the full model, which has all the interaction terms in there, and then you'd fit a reduced model, and you get these -2 log likelihood statistics, subtract one from the other, and that would be a chi-square statistic with the number of degrees of freedom equal to the number of interaction terms you test, right? Now, that's what you would do if you're using proc logistic. But if you're using proc GLIMMIX, you can't do that. There's a problem with taking the two, with starting with two models. If you had the same situation, interaction terms, and then you wanted to test for them, and you wanted to consider, fitting the full model and fitting the reduced model and getting from the output -2 log the maximized likelihood. Now, it would be -2 log the maximized of the pseudo likelihood based on the pseudo data. So you'd be using this approximation to get these -2 log R statistics, and you should be subtracting one from the other. Well, if you do that, you can get a bad and wrong answer. It's not correct to do that. So you can't, if you're doing a chunk test or any kind of a test, could just be for a single coefficient, and you're using GLIMMIX, what you have to do is you have to, instead of fitting two separate models, you have to fit one model and do what? What was the other way you could test a hypothesis in either, whether it was mixed or GLIMMIX? If you had several parameters you wanted to test, you do a contrast statement, right? And what you would do is you do a contrast statement, and you would write the variables you wanted to test after the contrast statement, and then you put a 1 and a comma in between the variables you wanted to, in between the variables you're testing, the interaction terms that you're testing, and that's what you have to do. And if you use the contrast statement, then the computer is doing the right thing. It's doing the right approach, and it has something to do with the pseudo likelihood thing that if you use the contrast statement, something goes right that would go wrong if you did the two models separately. So you have to use a contrast statement. That's basically what I'm saying. So if you're doing hypothesis testing, you have to use a contrast. In fact, if you're doing hypothesis testing, even when you're dealing with random effects, you basically have to use contrast statement also, which turns out to be equivalent to a mixture test. So anyhow, that's more or less what I wanted to say as sort of a review of what we said about GLIMMIX. But the last sort of thing we were spending some time on was this COVTEST procedure. So why was that such a big thing? Or why did I raise it or make the point that it's a new nice thing to have? And the reason why the COVTEST procedure is nice is because until 2 years ago, or really until last year when it came out, when it arrived in SAS, you couldn't really do a statistical test to evaluate anything about a correlation structure other than the Durbin-Watson test. And this COVTEST procedure allows you to do something you couldn't do before. Now, exactly how to use it properly is something I'm trying to show you, or I've showed you a little bit, and still trying to learn, as I'm going to sort of explain a little bit. So what I'm planning to do in the next 5, 10, 15 minutes is talk a little bit more about COVTEST and what it does and what it doesn't do. And then eventually, after maybe another 10, 15, 20 minutes, then I'm going to start talking about the main topic for today, which is multi-level modeling. That's the main topic for today. So I don't want to let myself not get to multi-level. We'll spend most of the class on that. But I want to talk about the COVTEST procedure. So let's talk about that. So I'm going to skip to this, wherever it is here. COVTEST, okay? And there are several different options you have when you want to use what's called the COVTEST option or the COVTEST statement to test for hypotheses about correlation structure. One of them is called the GLM option, okay? Now, if you use the GLM option and you write, after you put your model statement in and you write COVTEST GLM, what you're essentially doing is you're testing a hypothesis that the not only the R matrix in GLIMMIX, you're allowing you to consider both the R and the G matrix that you might use together in the same code, but the null hypothesis is that the overall correlation structure is independent. So you're testing independence. That's what you're doing, and so the null hypothesis is independence. And the alternative hypothesis is whatever R and G structures you're putting into your code, your model statement, not your model statement, when you actually write the random statements that indicate the R and the G matrices, whatever you've put in, that's the alternative hypothesis. So you're testing, when you use the GLM option, you're testing whether what you started with can actually be simplified to simply just independence. In other words, you're essentially asking is, do I really need to have to worry about correlation structure? That's what GLM does. Now, up until this thing came out, you couldn't even do that, okay? But that's one of several things, and I talked about some of the others. The diag-G option is one that basically says, well, if I have an R matrix and a G matrix that I've specified in advance when I wrote my model statement, the diag-G option basically says for example, if the G matrix is a 2x2 or 4x4 G matrix, which has variance components on the diagonal, but also covariance between various random effects on the off diagonals, the diag-G basically says that all those covariance parameters are zero. So it basically says the G matrix, the random effects in your model are all independent. So that's another way of saying that all the covariance values are zero. So if you say COVTEST diag-G, you're making that assumption about the off-diagonal elements in the G matrix. If you say diag-R, what you're basically saying is making the same kind of statement about the off-diagonals or the correlation coefficients in the R matrix, although you're not necessarily fixing anything or saying anything about the G matrix. Similar for diag-G. If you test diag-G, you're keeping whatever R matrix you put in. If you're testing diag-R, you're keeping whatever G matrix you put in. Okay, and then there's 0G, which basically tests whether whether you don't even need random effects. So if you say COVTEST 0G, you don't even need random effects. Okay, so that's a nice thing that wasn't available. Now, how you use these options to come up with some conclusions is sort of another story. And then there were some other features that I showed you last time that are even go into things a little bit more specialized, which which are even nicer. And I showed you this slide, and I want to talk a little bit about this slide and what this does. This is a slide where you actually have to write something like, you have to add something called test data, and you have to put in code in such a way to indicate the tests that you want to do that are, some of them are equivalent to like 0G or independence. But basically it allows you to do something a little bit further than that, because, for example, if you have and this is particularly, it's this one, and I talked about this one last time, .00. If you write .00 and you have a G matrix that's 2x2, okay? If the G matrix is 2x2, you see this picture over here, the G matrix down here at the bottom of the screen? The G matrix is 2x2. That means you've got a random intercept and you have a random slope. That makes the G matrix 2x2, okay? And it also says, unless you particularly use a default option, it also says that there may be a covariance between the two random effects, or correlation between, this is a covariance between the two random effects. And if you specify .00, what you're basically doing is saying, I'm going to test whether I don't need the random slope, but I'm allowing myself to keep the random intercept. In other words, I'm testing whether I can have a random intercept without a random slope. That's testing some subset of the two variance components that are in the G matrix. And the 0G doesn't do that. 0G, which would be equivalent to going 0, 0, 0, basically says there's no random effects. But this says, if I have two random effects, maybe I can test whether I can drop one of them. It's sort of like a backward elimination sort of type of approach to the G matrix, to how you can deal with the G matrix. So if you type, now just to make this point, is each one of these there are 4 lines. Each one of these 4 lines represent a different test. This one, 0, 0, 0, so there are 4 different tests being done if you write four lines over here. This one basically tests 0G. This one basically tests diag-G, because you see the 0 in the middle. The first dot represents the variance component for the intercept. The second dot represents, the second value in here represents the covariance between the two random effects, and the third dot represents the variance component for the random slope. And so if you have dot 0 dot, what you're saying is that this term is, you're testing whether this term is 0 and allowing these other 2 terms, because you're not specifying any value for them, the other two terms to perhaps be non-zero. So this is testing whether this is essentially diag-G. In other words, in the G matrix, there's no covariance between the two random effects. This is testing whether whether you can drop the random slope and the corresponding covariance, and just only have the random intercept. So let's say, for example, let's just take an example. Suppose it turns out you use this test, this third one on the list. Suppose it turns out when you do this test, it's significant. Suppose you go through the code, you code test data, and you look at there are 4 tests, but suppose you look at this one and it turns out to be significant. What do you conclude from that? What would you conclude from that? If it was significant when you tested this. This is what I'm going to make sure that you know what you're doing when you do this. Okay, what does it mean? Does it mean that you can just have a random intercept? You don't need a random slope? What does it mean? See, what's the null hypothesis? And what's the alternative hypothesis? The null hypothesis is that the random intercept is fine, you don't need a random slope. The alternative hypothesis is that you need both. That's what the alternative hypothesis is. Okay? So if it's significant, what does that mean? That means you can't conclude from that result that you can just have a random intercept and leave off the random slope. If it's not significant, then you could say you don't have evidence to suggest that you need a random slope. So you conceivably could just have a random intercept. That's what it means. So you have to make sure you know what you conclude when you do these tests. If you do this test with the 0, 0, 0, 0, and let's say that test is significant, what does that mean? Suppose you do the 0G test, and that means and it turns out to be significant. What does that mean? What's the null hypothesis? Null hypothesis is that you don't need random effects. The alternative hypothesis is that you need some random effects. So if this test is significant, then you can't conclude that you don't need random effects. You have to conclude, it looks like I need some, at least that's the best you can do at this point. You're not testing anything else other than whether you need random effect, any kind of random effect, or no random effect. So if it's not significant, if this test is not significant, this gives you evidence that maybe you don't need random effects. Now, there are other tests you can do that may change what you do, but if this test is not significant, maybe you conclude that maybe I need an R matrix, but I don't necessarily need a G matrix. Okay, so this is one type of thing you can do to help you test for when you've got a G matrix, and this is all essentially related to the covariance of the G matrix. this allows you to test with the G matrix whether the overall G matrix is significant, or you can look at subsets within the overall G matrix. Now, this thing that I have on this slide, which I didn't fully explain, but I explained a little bit, allows you to do something even more than that, and it goes beyond just G. It even allows you to deal with the R matrix, okay? Now, this particular example on this slide, this particular example is an example that helps, that illustrates whether you want, if you start out with an R matrix that's unstructured, and you want to see if it's, you want to test whether maybe it's okay to conclude that the R matrix is compound symmetric. Unstructured means that all the covariances are different, right? Compound symmetric means that all the covariances are the same. So this is a way you can do that, okay? And in order to be able to do that, I've got this example here where, and I talked about this before, so I'm going to try to do this a little bit again. Did I talk about this last time? I think I did. Okay. So suppose the R matrix is a 4 by 4 matrix. The R matrix is a 4 by 4 matrix. If I look at this next slide, here's a picture of what the R matrix. It's really not the R matrix. It's the R matrix, but it's the variance-covariance version of it. It's not the correlation. It's the covariance structure. This is the variance-covariance matrix. You notice the variances are on the diagonal, and they're all allowed to be different. And on the off diagonals, I've got different notation for the covariances, and they're all allowed to be different. So this is an example of what might be called an unstructured covariance matrix. So suppose I wanted to test whether that unstructured covariance matrix could be simplified to exchangeable. What am I essentially assuming? Well, I'm essentially basically testing whether all of these covariances, sigma 2,1, sigma 3,1, sigma 4,1, sigma 3,2, sigma 4,2, and sigma 4, whether they're all equal. If they're all equal, then I'm basically saying I have an exchangeable covariance structure, not an unstructured. So that's the null hypothesis. Null hypothesis is that, and so the null hypothesis is exchangeable, and the alternative hypothesis is unstructured. So if I want to do that, the way I do that using the COVTEST procedure, I write COVTEST, I give it a label. In this case, the label was unstructured versus compound symmetric, which tells me what I'm doing. And then I have to write something. This is the way that you have to write general, and then you have to put in some numbers. Okay? And these numbers are the numbers that allow the program or the COVTEST procedure to carry out this test, to compare whether, to see whether an exchangeable correlation structure is as good as the unstructured. Now, in order to do this, what you have to do is you have to recognize that the way the computer works, in order to figure out how it works, you have to be able to take the terms that are in this matrix, which is a 4 by 4 matrix, and you have to be able to sort of string out these terms as if it's a vector, right? You have to put it in one line, like a column vector, and that's basically what I did on this previous slide over here. You see where it says V, and it's got sigma 1 square, sigma 2 square, sigma 3 square, sigma 4 square. Those are the variances. Those are the variances that were in this, on the diagonal of this matrix. And then these are the covariances. And they have to be, the way this program works, and the way this COVTEST procedure works, it has to be in the order in which I've written them. I've got sigma 2,1, sigma 3,1, sigma 3,2. It can't be, you can't write it or assume that what you're doing is that you can't write it as sigma 2,1, sigma 3,2, sigma 3,1. If you do that, you're going to get all messed up. So you have to write it this way. And so it starts with sigma 2,1, and then it goes to the third 3, and then it gets up to the point where you're about to, after sigma 3,2, you have sigma 3,3, but that's sigma 3 square, and then you go to the 4th, and so on. So that's how you write this thing. And then what you're essentially doing, and if there's any place where matrix mathematics comes in, what you're basically doing is taking what's in this and multiplying it by this. Now you notice it says it's a row vector with a prime, which makes it a column vector. So if you multiply this matrix by this column vector, and you make the assumption that if there was nothing in here, these are all zeros for the rest of what's in here. I could have written zeros, 0, 0, 0, 0, but I didn't have to, in order to, the computer knows that if I didn't write zeros, anything after the last non-zero, everything else in every other column is going to be zero. So if I'm looking at this matrix multiplication and I'm multiplying this row, 0, 0, 0, 0, 1, minus 1, the rest are zeros, by this column vector, what happens is 0 times sigma 1 square is 0, sigma times sigma 2 square is 0, 0 times sigma 3 square is 0, 0 times sigma 4 square is 0, and then it's 1 times sigma 2 1 minus 1 times sigma 3 1. So, and then the rest are zeros. So it turns out that this row is essentially winds up to be sigma 2 1 minus sigma 3 1. And the second row is sigma 2 1 minus the third one down, which is sigma 3 2. And then it goes sigma 2 1 minus sigma 4 1, and so on. So if I take this matrix and multiply it by this vector of the variance covariances, I wind up getting a statement about my null hypothesis. And the statement is that these, in this case, 5 sets of parameters are all equal to 0. That's the null hypothesis. And if you just look at it, if sigma 2 1 minus sigma 3 1 is equal to 0, that means sigma 2 1 equals sigma 3 1, right? If sigma 2 1 minus sigma 3 2 equals 0, that means sigma 2 1 equals sigma 3 2. But if those two statements are true, then all three are equal, and so on. So what this matrix product actually winds up doing is it specifies a null hypothesis, which basically says that I've got independence. I'm starting with unstructured, and I wind up saying that all the variances are equal, all the covariances are equal. Now you notice that I haven't done anything about the variances. So what I'm doing is I'm leaving the variances, I'm allowing the variances to be different. So I'm still dealing with what's called the heterogeneous covariance structure, but I'm forcing the covariances all to be the same. So this is a way I can test using COVTEST whether there's a simpler structure than the unstructured that might work. And so if I do this test, just to make sure, if I do this test and it comes out to be non-significant, the test is non-significant, what might I therefore be able to conclude? Just want to make sure why it's worthwhile to do this. The test is non-significant. The null hypothesis is compound symmetric or exchangeable will work. And it's non-significant. Then I have support for that null hypothesis, right? If it's significant, what do I conclude? Well, I have evidence to show that I can't make the conclusion that the R matrix is exchangeable or compound symmetric if it's significant. You got that? I'm not sure if you got that. That's what this allows you to do, which you couldn't do before. Okay? And there are other things you could do. Now, let me just show you some of them. Now, first of all, I want to make the point that that if the R, and I did this last time, I'm sort of reviewing, but I know it, this is not that easy. So if you had an R matrix that was 4 by 4, this is what the V matrix would look like. If you had an R matrix that was 5 by 5, this is what the V matrix would look like. And if you had to use this procedure where you had to do this COVTEST procedure, you'd have to convert this matrix to a vector. And the way you'd convert it to the vector would be analogous to the way I converted it when it was a 4 by 4 matrix. But now I have to put, whereas before I had the 4 variances, there were 4 variances. Now I have 5 variances. So I have to put the 5 variances one after the other. Okay? And then I have to start the same way as I did here, sigma 2 1, sigma 3 1, sigma 3 2, sigma 4 1, sigma 4 2, sigma, just like I did before. But now I have a sigma 5 1, sigma 5 2, sigma 5 3, and sigma 5 4. So I have to add that. So the corresponding vector, I've got a capital V matrix, and a little v vector. The little v vector that corresponds to 5 by 5 is a 15 by 1 vector, as opposed to the little v vector that corresponds to 4 by 4 is 10 by 1. So if you want to actually test a hypothesis when you're starting out with an R matrix that's 5 by 5, so if everybody in your data set had 5 observations, then you would have to sort of consider this vector as, or this variance covariance matrix, and define the code that you'd have to use to do the test. Now, one reason why I'm saying this, I'm giving you this example for 5 by 5. You remember the FEV data set? The FEV data set that we talked about way back when. You know, that was when there was this pollution alert, and we had 40 subjects, and each subject was looked at, had their FEV measured over 5 weeks. Remember that? Okay. And we wanted to fit a model to that. And what model did we use? We used a linear model. Why did we use a linear model? Because the FEV was a continuous variable. So what program did we use? What program did we use when we started out talking about the FEV data? So we used mix, right? We used mixed. That's what we did way back in February or January. Okay. Now, could I have used GLIMMIX to do that? Could I actually have used GLIMMIX to have fit that linear model? So what have I been saying? The answer is yes, because GLIMMIX allows you to fit a linear model too. So I could have written the code in GLIMMIX form. Now, if I'm writing the code in GLIMMIX form, and I want to be able to say, I want to run the model to get an unstructured correlation structure, and I'm using GLIMMIX, do I write a repeated statement in GLIMMIX? No, GLIMMIX doesn't let us do, it only says random, right? So if I was running a marginal model, unstructured, and I want to use GLIMMIX to run a linear model, but it's an unstructured, what would I have to do? I have to write a random statement, right? Not a repeated statement, because GLIMMIX doesn't let you do repeated statement. And then I'd say if it's an R matrix, not a G matrix, marginal model, what would I say? Random residual, right? Because that's what you have to do to tell the computer that you want an R matrix. Then you go slash, then you say type equal to unstructured. That's what you'd have to do to run a linear model that way, okay? Now, in this case, this is not FEV. In this case, I've actually used, well, I haven't really said, in the model statement and the random statement, I don't really, this is assuming the correlation structure is independent, because I don't even have, I only have an R matrix, and the G matrix is 0, so actually, because I wrote unstructured, I'm assuming that I do have a correlation structure, and yet it's unstructured. Now, you notice that one other thing Zach and I just learned this morning. You notice where it says type equal to UNR as opposed to type equal to UN? And I wrote up here type equal to UN. What's the UNR? What's the R doing? Well, first of all, whether I wrote it as UNR or UN, it would be telling the computer that I'm really doing an unstructured correlation structure. But if I wrote it as UN, it would actually not be using a V vector that looks like this. It would be using a V vector where the variances are inserted into the, mixed in with the covariances where they sort of fit. In other words, the first variance would go before sigma 2,1, and the second variance would go, after sigma 2,1, and the third variance would go after sigma 3,2, and so on. It would use a different V matrix, but you could do the test either way. But in any case, all I'm saying is there's it's a little extra little trick for writing UNR. Zach, you want to say something? Add something?
And just to clarify real quick, so the different order that Dr. K is talking about, you can always look in the SAS output under the table that says covariance parameter estimates table. It's sort of near the end of your output, and the order that is in that table is the order that those variances and covariances appear in the vector. So the reason that it's UNR rather than UN there, they're both unstructured covariance matrices, and they're, as far as I can tell, the exact same matrices. It's SAS on the inside ends up listing those variances and covariances in a different order. And if you're wondering what order it's in, just look at the output, because that table tells you exactly what order SAS is considering these. So then you just switch around the ones and zeros that Dr. K has put up there, and you get the right answer.
You have to practice this.
You definitely have to practice.
The ASY, the AC code statement is the one that makes sure the computer gives you that information. Shows you the ordering that it's considering the variances and the covariances. But anyhow, so, okay, so that's one thing. Now, from this, let me show you a couple of other things you can do. Now, and I think I mentioned this, but we can go even further. But suppose I wanted to sort of test whether I started with an unstructured and I wanted to test whether it was toplets. An unstructured 4x4, and I wanted to compare it to a toplets that was a full toplets. In other words, look at the next slide here. This is a 4x4 unstructured, and I've got some color coding of red and blue here, but I'm leaving all these covariance terms, allowing them to be different here. But look in the bottom slide, in the bottom part of the slide, where the reduced model under the assumption that I've got a toplets matrix, so it's really a toplets 3, and because I'm allowing all the adjacent, the covariances that for observations that are adjacent to be one another the same, the covariance for observations that are 2 occasions apart are the same, and I'm allowing the only single one that's 3 variances, 3 occasions apart to be different from the others. And so that's toplets, and it's really, in other words, in terms of the term stationary 3 dependent. And that's what when you write toplets, that's effectively, so suppose I wanted to test stationary, I wanted to compare, I started with unstructured, but I want to see if I can simplify it to stationary 3 dependent, okay? So how would I do that? Well, look at this code. Now, we're starting with unstructured. So an unstructured, and again, it's 4x4, and this is the little v vector, same little v vector as we previously used when we were going from unstructured to exchangeable, but now we're going from unstructured to toplets, or stationary 3 dependent. Now, so notice that the code that I've written here, or at least these numbers that I've put in, it's not the same set of numbers that I had here. It's a different set. So what does this mean? Well, if you look at this thing and you think about it, it's, again, whatever's in here is multiplying by that vector. So you're doing matrix multiplication. So this is one thing you want to make sure you remember how to do. If anything in the course you need to remember how to do is matrix multiplication if you wanted to do something like this. So if you're looking at the first row here, and you look at the first row and you're saying, well, what is that evaluating, the first row? Well, what you're doing is you're multiplying what's in the first row by this column vector. And the first row is 0, 0, 0, 0, 1, 0, minus 1, 0, 0, 0. I didn't write the zeros, but the rest of them are 0. And if I multiply that row by the corresponding column vector, I'm talking about sigma 2, 1 and sigma 3, 2, because this is sigma 2, 1, this is sigma 2, 1, this is sigma 3, 1, and this is sigma 3, 2. So I'm comparing sigma 2, 1 with sigma 3, 2. And if I do this, I'm comparing, now what about this one? This is sigma 2, 1, so what's this one referred to? This is sigma 3, 2. And this is sigma 3, this is sigma 2, 1. This is sigma 3, 1. This is sigma 3, 2. This is sigma 4, 1. This is sigma 4, 2. So I'm comparing sigma 3, 1 with sigma 4, 2, which are 2 occasions apart. 3, 1 versus 4, 2 are 2 occasions apart. So, so that's what I'm comparing. And then if I actually do this, it's sigma 2, 1. And then this is what? 2, 1, 3, 1, 3, 2, 4, 1, 4, 2, 4, 3. So it's sigma 2, 1 minus sigma 4, 3. So that's what the third row is doing. So if I think about what I'm testing whether what comes out when I do this multiplication is all equal to 0, then sigma 2,1 is equal to sigma 3,2. Sigma 2,1 is also equal to sigma 4,3. So these three are equal. Sigma 2,1, sigma 3,2, sigma 4,3. Adjacent observations that are right next to one another. 1, 2, 2, 3, 3, 4. Okay? And then sigma 3,1 minus sigma 4,2 is equal to 0. So I'm setting that sigma 3,1 is equal to sigma 4,2. So what I'm actually doing is, by writing this code, I'm essentially, the null hypothesis is Toeplitz. So if I write this code and I carry out the computer and I write this code and I write COVTEST and then I say run, I'm going to do that test. I'm going to be able to compare whether a Toeplitz stationary, in other words, a stationary M3 thing, is at least as good as an unstructured correlation matrix. If I get significance, then I can't say that the Toeplitz is better than unstructured. If I get non-significance, I can say, well, maybe I could use Toeplitz. So that's what I'm doing. Okay. Now, what about this? What have I done on this slide? This is one of the extra slides I sent you on Friday. What's the difference between what's here and what's here? Well, if you look at the numbers here, there's an extra line over here, down at the bottom. There's an extra line at the bottom. This has got three rows or 3 lines, and this has got 4 rows or 4 lines. The first 3 rows are exactly the same. The 4th row is different. What's this comparing? If you look at it, you have to think about this a little bit. If you look at it, this is something where experience is going to, you have to work with this a little bit. But what is this doing? Well, this is the first 4 are the sigmas, or the variances. This is sigma 2,1. This is sigma 3,1. And this is what? Sigma 3,1. Sigma, is that right? Sigma 2,1, sigma 3,1, sigma 2,2, sigma 4,1. This says sigma 3,1 equals sigma 4,1. Sigma 3,1, go back to the original, sigma 3,1 is equal to sigma 4,1. And if the rest of it is true, then what I'm essentially doing in this, what I've now essentially done by this, adding this extra line, is I'm doing something a little bit stronger than testing for stationary m equal to 3. I'm saying that these 3 are the same, and not only are these 2 are the same, but these 2 are the same as this one. That's what I'm essentially doing. So if I'm worried about whether, if I want to test whether maybe these 3 are the same, and once I get past this, these 3 are the same, then I can add this extra line to it. And that's what I'll be testing. I'll be testing whether these 3 are the same and these 3 are all the same, as opposed to these 3 are the same, these 2 are the same, and this one's different than all the others. Question. All I'm trying to say is you can do some things here that you couldn't do until you had this thing available. Okay. Now, now let me just tell you something. This is all conceptual in some sense. I'm showing you what the code would be, what you'd have to do if you wanted to test this. Could you actually do it in practice? Okay. So today, I didn't start this until today because I'm learning this as we go along. What I started to do today, and what I did to a certain extent, is I basically said, well, let's see if I can do this using a data set. And I can do some of these tests using a data set. And the data set that I used was the FEV data set. And I actually ran through that, and I've sent you something that I won't have time to go over today, but there's something that you could look at. It's on Blackboard that shows you a code, a bunch of codes with the FEV data set that shows you how you can apply this. Okay, so anyhow, I'm just going to go just a little further, and then we're going to start multi-level stuff. But let's look at these 2. So suppose I call this hypothesis 0,1. Suppose I call this hypothesis 0,2. And suppose it turns out that the first test is not significant. What do I say? This test is not significant and this test is significant. And I have a question. What would you conclude? Suppose you do both these tests. You want to use you know, this feature to try to come up with some conclusions about the correlation structure. Suppose you do both these tests, and this one is not significant, but this one is significant. What would you conclude? Well, first of all, would you want to conclude that you needed an unstructured, unstructured R matrix is what you needed? The answer would be no, because one of them was not significant, right? One of these two is not significant. So if this is not significant, if this was not significant and this was significant, what would you use? This one or this one? You'd want to use this one, because this basically says this doesn't work. If I do this test, I get something significant. If I try to test whether this way of looking at the correlation structure is what it should be and it's significant, and say I can't do that. It doesn't work. Whereas this test said, fine, this is not significant, so I can use stationary m equal 3 as opposed to stationary m equal to 3 plus this extra thing about the extra term being the same as the other two terms. Well, if it turns out the first test is significant, whereas this test is not significant, what about that? What if this test is significant and this test is not significant? Which one would I go to? I've got three choices. The three choices are unstructured, that's one choice. The other choice is stationary 3 dependent. And the third choice is stationary 3 dependent with this extra thing here where all three of them are equal, not just two of them. What would be my answer? Whoops, that's not what I meant. Well, my answer, wait a second. My answer would be, I choose this one. Okay. Now, if both tests are not significant, what do I do there? Both tests are not significant. This is not significant, and this is not significant. Well, either one is okay. I haven't proved that one is better than the other because I'm not comparing these two. This one, but I'm basically saying that I don't need an unstructured R matrix. One of these hypotheses is better than an unstructured R matrix. You follow what I'm saying here? Just the logic here. If both tests were significant, if both these tests were significant, what would I have to conclude? What would I have to conclude about the R matrix? About the R matrix in terms of the three choices I have. I'm only comparing three choices. Unstructured, stationary M3, and stationary M3 with a little extra juice in there, you might say. What I'd have to say is I can't choose either one of these two if they're both as significant. So as far as I'm concerned, I don't have evidence to reduce the model below unstructured to either one of these two. It doesn't mean that there isn't another structure that I couldn't test. But at least I can't, if both of these are significant, I can't use a simpler R structure than unstructured. At least I don't have evidence from these tests. So that's what I'm trying to tell you what you can do. Now let me just show you one last thing. I think this is the last thing I was going to show you, yeah. Last thing. Now, suppose I wanted to test stationary m equal 3 versus stationary m equal to 2. Suppose I wanted to do that. M equal 3 versus m equal to 2. Okay. How would I do that? In terms of the logic of this thing, I don't know whether it works or not, because you have to practice to work, but think about the logic of it. So stationary m equal 3. Now look at the model statement here where it says model y equal drug time. This is just a test thing, but look at the random residual. See where it says subject equals should be subject equals subject, type equal to toplets, whereas previously I had type equal to unstructured, or UNR. I should have been UNR, but now I've got type equal to toplets over here. So what am I starting with? You see on the screen here, I'm starting not with unstructured. I'm starting with toplets. When you write toplets, it's equivalent to stationary m equal to 3. Stationary 3 dependent when you got a 4x4 matrix, 4x4 covariance matrix. So if I say R is toplets, so if that's my starting point, and I want to test to see if I can drop one of the terms in there, I can simplify it. So what do I mean of simplifying it? Look at this. If I'm starting with toplets, stationary m equal to 3, and I want to look at stationary m equal to 2, what I'm comparing is this matrix versus this matrix. What's the difference between what these two pictures say? What's the difference? There's a 0 here, right? There's a 0 here, correct? So what I'm basically saying is, if this is 0, then I'm really at stationary 2 dependent. So how would I code it in order to make that happen? In order to code that to make that happen, at least the logic of it, as far as it makes sense to me, again, whether it works or not, but the logic of it would be to say, look, I'm starting with stationary 3 dependent, and I want to set this one to be equal to 0. This one, sigma 4, 1, which is this one in this whole vector thing, it's the third from the end. And I want that to be 0. So what I could do, what makes sense to do, is to say, here's the third one from the end. I've set it 1. So if everything, and I only have one line here. The reason why I have one line and not several lines is because if I'm assuming I'm starting out with toplets, stationary 3 dependent, it would seem logical to me that I only need to make one test within that. And the test would be to focus on whether this sigma 4, 1, which is setting it equal to 1, is equal to 0. If that's the case, and I multiply this by the vector, I wind up getting sigma 4, 1 equal to 0. So that's what makes sense to me to be the null hypothesis that you could go. So what I'm trying to say is this COVTEST procedure logically allows you to even test for subsets of R matrices, which is something, again, I keep saying this, something that we couldn't do before. Now, whether this works or not, or how to make this work, is I'm not completely sure. Zach?
I was playing around with just this issue literally right before
This
we came to class.
example.
With this kind of example. Well,
Yeah.
what I did was I ran a GLIMMIX model with the Toeplitz R matrix. I think I ran it on the FEV data, so it would have been a Toeplitz stationary 4, because there are
Right.
5 observations in FEV.
Right.
And what it did is in the covariance parameter estimates table that I mentioned earlier, it only gives 4 estimates for observations.
Because it's stationary 4.
1, 2, 3, and 4.
Right.
So it may be that rather than that long matrix that you've written out,
It may have to be shorter.
it may actually be shorter. So if you
Right.
wanted to get rid of, if you wanted to go from, say, stationary 4 to stationary 3, you might just write 0, 0, 0, 1, as
Right.
opposed to all of that. But I think all of this general COVTEST stuff is based off of what the covariance parameter estimates table says.
Right.
So always look at that to get an idea of what kind of matrix you're writing.
But I tried this too, and it didn't make, I couldn't find what I was looking for, I couldn't find it. And when I ran it this way, although it's logical to me to write it this way, it didn't work.
Yeah.
So I'm not sure how to make this work. When I ran the other things, what I've described up to this, everything worked using the FEV, but this didn't work. So it seems to me there should be a way to do it. So the main point of all this, the main point is that COVTEST is a method to allow you to do some things you couldn't do. I've said this already 10 times already. Okay. Now, some of the things you can do, I know you can do. Some of the things I think you can do, but I'm not sure exactly how to do it. Okay. And when you're working on your project, that's something you ought to play around with to see what you can do, because you may be able to figure out some things out that that will make your project better, is all I'm saying. Okay, so with that, I am going to stop talking about COVTEST and stuff, and I want to get to the main topic of the course, the main topic of today, which is multi-level, which is what we really need to do. So are there any questions? And I know if you don't have any questions, that doesn't mean you perfectly understand everything you have to do, because the only way you're going to figure out how to get good at this is to do it with some data. And a good way to do it is to try the FEV data set. In fact, I guess maybe before I do multi-level, the last thing I'm going to show you is, let's see if I already put this up here. Yes. There is an extra PowerPoint presentation that I added, and it's called, it's got a title, 10A1 COVTEST. It's on Blackboard, but it's not something I sent you. But what I've done here in this extra presentation is I've applied what I've just been talking about to the FEV data set. And what I've basically done is I've said, well, the FEV data set, just like Zach said, remember, there's 5 observations per subject because there were 5 weeks. FEV data set, every kid was looked at over 5 weeks. So you're talking about a 15 by 1 V matrix and a 5 by 5, 51 V vector and a 5 by 5 V matrix. And if you wanted to use the correct code to test whether whether you can have an exchangeable correlation structure as opposed to an unstructured, this would be the right code. And you should try it between now and next week or whatever it is. If you want to see if it works, try it. It will work. This one works. And this next one works. Let's see. This next one works too. This is the one that compares unstructured to toplets. This one works too. But then I tried toplets versus toplets, toplets 3 versus toplets 2, and I tried some things, didn't work. But anyhow, this is something you might want to, this is a homework assignment that I haven't given you, and it's not really a homework assignment. It's something that you might want to do to help you deal with some issues about how COVTEST works. Okay, so with that, I want to do 5 minutes, then we take a break. I want to introduce multi-level, and then we take a break. Okay, so here we go. I got to say something about it before we take off here for a little bit. Multi-level modeling. Okay, let's talk about what multi-level modeling is. It's a very easy idea. That's why I want to, but it's not that easy to do in practice like everything we've just about been learning in this course. In practice, it's not as easy as it might seem to appear. Okay, what we're talking about a multi-level analysis is what I write here. The study of effects of collective or group characteristics as well as individual ones on individual level outcomes. Okay, what this basically means is when you're talking about a multi-level analysis, you're talking about a data set and a modeling situation. You're typically doing some modeling, a modeling situation where the variables that are going in the model as predictor variables, as the independent variables in the model, they are variables measured at different levels. Different levels of, for example, one level would be at the individual level. Something about a person's weight, their age, anything else, their body mass index. That's an individual level variable. You might also have another variable that's not measured on the individual, but it's measured on, for example, they go to a school, and the question is what's the size of the school? How many kids are in the school? Something like that. Or what location? Where's the school? Is the school in the northeast, south, or west of the state or in the country or something like that? That's a school variable. Okay, so we're talking about an individual variable and then another level. And then it could even be a higher level than the school. It could be the schools are within, it could be something, the schools are from a state, and it could be a state measure, some measure of the income, the average income in a state. So you could have variables measured at different levels. So what a multi-level model essentially is a model that in the predictor part of the model, you're allowing yourself to have variables that are measured at different levels. And it doesn't necessarily say that the model has to involve correlated data. That's where you have to work with this to determine whether it does or it doesn't. If you just put these different variables in the model on the right-hand side and you assume everything's independent, that may work, but it may not work depending upon what conclusions you want to make or what decisions you want to make about what you're going to say about multi-level. So, as I say, a large proportion of current epidemiological research is based on the assumption that distribution of disease in population is explained exclusively in terms of individual level characteristics, but doesn't have to be. It might be based on not only individual but other levels. Okay, and if it's based on other levels, then you're talking about a multi-level or a contextual situation. If it's only on the group level, then you're talking about ecological, on one particular group level, the state level. If it's only on the individual level, you're making individual level conclusions, okay? But if you've got group and individual level, then you're talking about a multi-level, and in sociological terms, that's called contextual. That's another term for multi-level, okay? Got that? So let me say a couple of other things. So why do we do this? Well, I basically already said, is that it may turn out that if you ignore group level variables, then you're missing something. You're missing the boat on what you're trying to draw conclusions about a study questions. So that's why we want to consider multi-level. Ignoring the role of these group levels, these group or macro level variables, may lead to an incomplete understanding of the determinants of disease in the individuals. That's why people are always considering or worried about, maybe I should be looking at, if I've got things on another level, I ought to include them, because maybe I'm missing something in terms of what's going on in terms of my question, my research question of interest. Now, I'm almost done before we take the break. Now, I want to say there are two types of group level variables. One type is called derived variables, and the other kind are called integral variables, okay? Derived variables are like, suppose you have a bunch of people in a group, and you've got their individual, incomes, okay? How much they're making. Suppose these are adults and they're working, okay? So you have their income for a given year. Well, you have the individual income. If you want to get a derived variable, maybe you average the income. So you have the average income for any one of the groups that you're interested in looking at. So you have the average income for this group and an average income for that. That's a derived variable. A derived variable doesn't have to be an average. It could be, for example, it could be people in a group. It could be the proportion of the group that are male. That's not an average. It's a proportion or percentage. Okay, so derived variables could be percentages of what you have on individual variables. At the same time, integral variables do not have analogs at the individual level. It could be that you've got a variable that has to do with, well, everybody comes from a certain neighborhood. Does this neighborhood have a certain kind of health system or a certain kind of health care approach in that neighborhood? Is there a health care, is there a hospital in that neighborhood, or is there some kind of a health care facility in that neighborhood? Yes or no? Well, that's not on the individual, that's on the neighborhood. So you can have an integral variable. So when you have these different kinds of variables, it may be either one or both of variables that you want to consider if you want to answer a research question. So that's sort of when we're talking about multi-level. Now, the problem is that when you talk about individual level outcomes within groups, if you've got these variables measured at different levels and you're looking at individual level outcomes, they're often correlated. You have to take that into account somehow. So correlated data analysis is required, and what typically happens is mixed models, like we're talking about with GLIMMIX or mixed, typically have to be fitted. So it's 10 of 4. 5 after 4, we'll start talking about the details of this, how that's done. But that's the idea, and it's a simple idea. So the idea is you got a bunch of variables that are at different levels, measured at different levels. You throw them into the model as predictive variables. Now, you might have to take into account correlations, and that's what we're going to look at after the break. 5 after 4, okay? And we've got lots of examples and stuff to talk about. You want to take a break? Yes. You do. You just sort of totally, I don't know, totally what? Okay, so let's pause. Okay, let's talk about multi-level. Now, one question is, how many of you have learned something about multi-level somewhere or other in the past? Another course? Anybody? Andrew, what course?
Also, cluster analysis.
The cluster analysis course?
No, not. Oh, you're asking what course?
No, yeah, you've learned it somewhere.
Not, I've heard of it in other courses.
You've heard of it.
My question is, like,
Okay.
modeling involving cluster analyses.
Modeling involving cluster analysis is what this whole course is about, okay? Now, this is where you've got, now that's not your question,
Not really, but
okay? Well, you have you're dealing with clusters when you're doing multi-level, but you've got like clusters within clusters. And so you got more of a problem trying to figure out what the model should look like and how you should fit the model. That's what we're gonna kind of work through here. Is that,
yeah, I was just making sure that I understood.
okay, okay. So you don't, none of you or most of you haven't heard this or haven't done anything with this. It's, again, it's really not that bad because if you think about it from the conceptual sense, you got predictors in the model that are measured at different levels, but when you start trying to work through it, it's a little bit complicated. So let's talk about the ways that you do multi-level modeling. And there are usually three ways to approach how to do multi-level modeling, okay? One way, which is what a lot of people like to do if they want to get things exactly sort of cross their T's and dot their I's, so to speak, is to write separate regression equations at each multiple level, at each level. In other words, if you got an individual level, you write an equation at the individual level that only, like a model at the individual level, and the only predictors in that model at the individual level are individual level predictors, like a person's age or their sex or something of their BMI or something like that. And at the next level, the only variables, you write a model, but the only variables you put in at the next level are variables that are measured at that level. So it might be at a school level or a county level or a state level or whatever it was, and the only variables are not at the individual level, at the next level. So that's the idea in terms of one way of doing it, write the separate equations, okay? Another way to do that is, in fact, there are programs, but SAS doesn't do that this way. There are programs that if you specify what the model looks like from the three different levels and you put it into a certain program, it'll do all the work for you, supposedly, as long as you specified the models reasonably. In other words, you do the problem, the three models or the five models, whatever it is at the different levels, and you crank it into your computer program, it may work everything out for you. Another way to do it, starting this way, is you write a model at each of the different levels, individual, higher level, next higher level, and then what you do is you combine the information, you combine the models and get one model that combines all the information or combines the information that you put in the three separate models, and then you use that one model to decide on what program you're going to use, whether you need correlations, what those correlation structure is, and what the code should be for your program. So the second one says, do it separately, but then combine them. And the third one basically says, don't bother with that. Just write a single model. Take the variables that you're dealing with, put them into the model in terms of what you think are reasonable, and then somehow decide a correlation structure that you think might work. And that's the third way. Now, of these three ways, the one that most of us do here in the School of Public Health, or the one that's more amenable to what we do in the School of Public Health, is the second one. So that's where where you write the models separately, and then you can combine them into a single model. So that's what I'm going to talk about and illustrate. And there are different computer packages. SAS's ProcMix, ProcGenMod, and GLIMMIX, and even a procedure called NLMix, which we're not going to deal with because it's not really hardly ever used anymore, all allow you to do multi-level modeling, okay? But there are some other packages. There's a package called HLM, Hierarchical Linear Modeling. It's a package that apparently I think is in the SAS, if you work at CDC, how many of you have some jobs at CDC, you go there? Work at CDC, I think it's in the CDC system, HLM. Okay, so that's another option. And that procedure, that package allows you to put in the models separately and let the computer do the work for you in terms of not combining and doing whatever. And then there's another program called MLWin, which is, I'm not sure if SAS has it, but there are some other programs. But we're not going to really do that because we're primarily familiar and comfortable with SAS, but there are other things you could look at. There's even a program called WinBugs that some people swear by is the way to do that, way to do this, and I've never used it, so I don't know how it works. But anyhow, I've referenced these. So let's talk about the particular program, although I have some examples of taking SAS information and running it on SAS and running it on HLM to see whether I get similar results, and typically you get similar results, or almost the same results. So that's what you'd hope, okay? Now, to talk about what a multi-level model is, we're going to just focus on an example. And we're going to write a two-level model, 2 levels, so that at each level there are some variables that are going to go in the model, and they correspond to measures of whatever the levels are at each one of these levels, the measures at each one of these levels. So we're going to use we're going to do it by linear regression, but even though we're going to consider some other ones, some other models, and we're going to consider data collected in J schools. J is the number of schools. J could be 10, I'm not sure, but and there are N sub J pupils in the Jth school. Pupils, students within the Jth school, okay? The dependent variable is the pupil career outcome. So somehow we've got information about, even though we've got information information on the school, kids within schools, the outcome variable is what happened to this kid later on in their career. Something that they've achieved, or could be their could be their income. Okay, and we've got pupil level predictors, individual level predictors like the SES score of the individual. And then we've got school level predictors like the school size. So these are an example of 2 different measures at 2 different levels, just to take a simple example. Now, in general, you could have a whole bunch of these variables and a whole bunch of these variables. And you could have more than 2 levels, obviously. So let's look at it from 2 levels and see how it works. Okay, so, and let's talk about it in terms of setting up models at different levels. Okay, so what you do is you set up a separate regression equation within each school to predict the dependent variable y by the pupil or individual level predictor. And then across schools, the regression coefficients will vary and have a distribution with some mean and variance. So I'm starting with the first step, which is on the individual level. So I have a model, and it's a linear model. So is it a linear model? That's not what I wrote there. Did I say linear model? Linear regression example, but I didn't write it that way. Well, could be a logistic regression. Let's just figure out that it's so the model it's a logistic model. The outcome is some pupil level career. Did they make a lot of money or not? I guess is the way, or whatever the outcome is, success or failure, Supreme Court justice or not, right? It's a joke, right? Anyhow, so the first level, you notice that I'm writing the model for the outcome variable, but since it's a logistic model, I have to use a link function. And the link function says the model is the logit of the mean is a linear function in an individual level variable. So X stands for an individual level predictor, okay? So then once you then do that, you then say, well, look, I've got this, I'm going back to this again, I've got this individual level predictor, but now what I have is, what does this mean? This is the logit of the mean for the ith student within the Jth school, okay? And this is the value of for a particular student, the ith student within the Jth school. And if it's a model for the individual, then the coefficients in this model are going to be, if you think about the label, the intercept is going to be beta 0j, because beta 0j depends upon the Jth school. So the observation on the ith individual for the Jth school is going to have an intercept for the ith individual in the Jth school and the slope, if we're just considering a simple linear model there. Okay. Now, what we're then going to say is, okay, that's the model on the individual. What can we say about the school? Well, we have these two parameters, beta 0j and beta 1j, which are school level parameters. So what we're then going to do is we're going to write a model for each one of these parameters. And what we're going to do is we're going to, and in terms of school level variables. So beta 0j is equal to some linear model involving, and in this case, we're going to only consider one school level predictor, z, and this is going to be the linear model for beta, the intercept, and the linear model for the slope. Okay, and there's only, we're only illustrating it for one, to keep it simple, for one group level predictor. So we've started this way, and then we've stretched it. Now you notice that in order to go from the beta, from the individual level regression coefficient to the school level, we now have to consider different parameters for the school level. So you notice the parameters here are called gammas now. I have to change the name of the parameter, but this is an error term, and this is an error. I'm allowing myself to have error terms at the individual level and at the school level. Okay. Now, what do we do next? Well, we have to combine the two. How do we do that? Well, what we do is we write a single complex regression equation by substituting the second step equations into the first step. So the first step was this. Okay. Now, beta 0j, going back to this, is equal to this. So I'm just replacing it by this, and I'm replacing beta 1j by this. And then I'm working out the algebra until I get this final model. Okay, this is the final model when I work out the algebra. What's in the final model? Well, I just had to combine terms, and I've now grouped it in a certain way. Now, you notice the way I've grouped it was there's an intercept part of the model, there's a slope part of the model for the x variable, there's a slope for the z variable, and there's a slope for the product. So what's come out of the specifying these separate models is the variables that were at different levels, but they come into this overall model because I'm combining the two. So this overall model involves the variable at the individual level, the variable at the group level, and the interaction of those two. And it also involves, you see the U0j and U1j, these are random effects. These are random terms because they come out of the second model. And you notice that the E term is not in there because we're talking about logistic, although it is in there in terms of this original model. Okay. So if you had this situation, what would you say? If you wanted to, if this was your model, okay, and you were doing this is a logistic model, and you were going to run a program to do this, what program would you use based on everything we've said so far? It's a logistic model. Mixed? No, because you can't use linear model for mixed, right? So it would be GLIMMIX. Would it be GenMod or GLIMMIX? Why wouldn't it be GenMod? Because you've got these two variables in here that are random effects. These are random factors. So you can't use GenMod. So this is a GLIMMIX model, right? Now, if you decided that there really wasn't any error in terms of these, or one of these really wasn't an error, then maybe you are getting back to GenMod. But in any case, that's not what this results in. So this model contains a random intercept and a random slope for the individual variable x. Random intercept and a random slope for x, but it doesn't contain a random slope for z, and it doesn't contain a random slope for the product term. Now, if it contained these extra random slopes, then you'd have a more complicated model. And it could, but that's not what I've done. I've just made it to try to illustrate it. So what do you do with this model? If you had this situation, what would you do? If you're using GLIMMIX and you were going to write the code for GLIMMIX, you already have enough information from this model to know what to write. You write proc GLIMMIX, you write the model statement, you put in the fixed effects, and then what would you do for you put in the fixed effects, and then how many random statements would you have? How many random statements would you have? Well, if you wanted to consider an R matrix, you wanted to consider. Now, why would you want to consider an R matrix? It's not clear why you want to consider an R matrix, but if you wanted to consider the fact that you had two random effects, you'd have a random statement without a residual, and then you'd have random intercept, and then you'd have random intercept, and then you'd have whatever the name of the X variable is, random intercept X. Well, let's look at the next slide. Let's see if I did that. Let's see if I did this. That's what look what I've done in the next slide. I actually have two different ways of writing the model, but you notice I've got GLIMMIX, okay, method RSPL. I didn't talk about this very much just in previously today or last time, other than say that this is the general method that most people use that has better properties than some of the other ones, even though there's some debates. But anyhow, the model has y, x, z, x times z. That's the model, right? Those are the variables at these different levels. I've got random residual. When I write random residual, what am I essentially doing? What am I saying about the R matrix? R matrix is independent, right? If I didn't write random residual, what would be the R matrix? If I just left this off, or left off random residual, what would the R matrix be? Still be independent, okay? Okay. However, if I left off the random residual, left it completely off, I'd have this problem with this over dispersion thing that I wouldn't be dealing with that I mentioned last time. So I recommend you, even if you don't have, even if your R matrix is independent, you should write random residual. And then it's got random intercept X. Then it's got subject equals school, G. What's G stand for? G stands for the G matrix. It's asking the computer to give you an estimate of the G matrix. So what your R matrix is independence, and your G matrix is a 2x2 G matrix. And so I've taken what is a multi-level model, and I've written the code for that. And I've basically said subject equal to school. Now, one of the tricky things that I'm not sure if I completely know the answer to all this, but you notice at the bottom of the screen here, I've written almost exactly the same thing, but then I said student parentheses school. Why did I do that? Why did I do that? If you think about the way the data is, okay, each of the students are located within a given school. So it might make more sense to write the statement this way, student parentheses school, because that's what it means, students within schools. Okay. In this case, I've just said subject equals school, and I haven't said that. So question is, would I get a different answer, depending on how I did it? It turns out it doesn't matter. In this case, it doesn't matter. Now, when it does matter is when I'm not completely sure. That's where I have to spend some time. I've never quite figured that out, exactly what to say, but this is something where you have to read the user's guide among all the things you have to do and try to figure out what it is. But it doesn't matter, and if it didn't matter, whatever you did, then who cares? Okay, so either way is going to work, but that's how you do it. That's simple example. Okay, now, however, okay, now I said, so the second step that we just did was I started with this model for individual, and then I started with the second level model, and then that was the second step, and the third level was combining them. Now, I could have, this is where the sort of problems, complications come in. I wrote the second step this way, but did I have to write it this way, even if I only had one Z? Suppose, for example, I wrote the second step this way. Suppose I wrote the second step this way. Previously, beta 1J, in addition to this, had a U1J, right? Suppose I wrote it like this. Suppose what I'm saying is there's an error if I'm talking about the intercept, but as far as I'm concerned, I'm not worried about the slope. There's no error. If I can predict the individual level, if I predict the, this would be the school level variable on the slope, I'm not worried about. Now, whether I know this or not, I don't know. I'm not sure what to do. But if I do this, if I use this as my second step, and I combine the first step model with the second step model, I combine it, this is the model I get. Look at the bottom of the screen. What do you see in the model? How does it differ from the first model? How does it differ from the first model? It's got a random intercept, right? Does it have a random slope? You see U1J in there? The reason why you don't see it is because I didn't start out with that, okay? So the third step, the second step is like this, and I combine the thing, this is the model I get, so what would be the code for this? I think I have it on the next slide. Yeah, I do. The code would be for this, would just have random residual, random intercept, but it wouldn't have random X. Previously, it had random intercept X, okay? Why would it have just random intercept? Because that's all I have, okay? So what I'm saying here, this is the sort of inherent problem in doing multi-level modeling. If you're going to model a situation where you've got variables measured at different levels, what you have to do is decide how to, at the different levels, what the model looks like. And depending on what you decide to put in the model at these different levels, how you define the model at these different steps, you're going to get a different overall model and a different code that you're going to use. And that's the sort of inherent problem in multi-level analysis. That's where the problem comes in. So, but that's something you have to decide. Now, if you decide that, as far as you're concerned, you don't like this second step, or you're not even sure about the first step versus the second step, you could just say, well, look, I'm going to start with this model. I'm going to start with this model that allows for random intercept and slope and allows for the most general situation I want to do. And I'm not going to go from one level to another level. I'm just going to decide on a model and random effects that I think make sense. That was the third alternative. Remember, the first alternative is state the model at different levels, let some program do it. The second alternative, state it at 3 levels, combine them, and then figure out what the program code should be given how you've combined them. The third one says, just choose the model that you think makes most sense. And if you think the model should have a random intercept and a random slope, do that, okay? And there's no right or wrong answer to this. Just like there's hardly any right or wrong answers, almost any modeling issue that we do when we do. I mean, there are better choices than other choices, but there's never any, you're never actually sure. It's an it depends situation. This is an it depends situation. What you do for your second step and even what you do for the first step varies. So that's the idea. Questions about that? That's the idea. Now I'm going to go through some other examples, but that's the idea to illustrate some of the other steps. Okay. So so we just illustrated the alternative one. Now I want to talk about a different example. And some of the people in the class are working on this example. Who's working on this example? It's Mark? No. There's a group working on the Gimme 5 data set. It's you guys there in the front. So am I doing the project for you right here and now? Go for it, right? Okay. Well, we're going to talk about it, but you have more stuff in your project stuff to do than I'm going to talk about. So you do have extra stuff to do here. So, but anyhow, you're doing this. This is a data set, and the idea is very, very simple. You know, we try to get people in general to eat more fruits and vegetables because it's better for your diet. So this is an example of an intervention study in school systems to get kids in school systems to eat more fruits and vegetables. That's the idea. Okay, so there were 16 schools. 8 of them got an intervention where there was all sorts of advertisements to eat more fruits and vegetables spread all around the school, and the other 8 schools didn't get anything more than you usually get if you watch television or you just talk to your parents or somebody else, your friends, who said it's better to eat more fruits. So there wasn't a special intervention for the control groups. Okay, so you had these 2 kinds of schools. Okay, intervention and control. Okay, and then within each school, within each of the 16 schools, 10 kids were sampled or drawn in some random way. I don't know if it was really random, but it's a real study. So there were 10, and I'm not sure in your study that you guys are doing whether that's with a really 10. I'm not sure, but anyhow, there were 10 students from each school, and in this example, each of these 10 students were asked at 3 different times over 3 weeks how much fruits and vegetables they ate, some measure of how much fruits and vegetables they ate. It's sort of a count. It's a count. So when you think of count, what do you think of as a model? Poisson, right? So it makes sense that you probably do Poisson, not logistic, and not linear, because it's a count, okay? So what's the question? What's the main question? So you got a baseline, post 1, post 2 for each of the, you've got 3 measurements for students within schools, and then you've got 8 schools getting experimental, 8 schools getting control. Okay, the idea is, the key question is, do the kids in the experimental schools tend to eat more fruits and vegetables than the kids in the control schools? It's a simple question, right? So how do you do this? Well, you've got individual, you got 3 measurements within each school on each kid. So at a certain, at 3 different times, you've got 3 measurements. And then you got on each school, on each individual, you've got maybe an individual characteristic of the individual, which I haven't mentioned here, but it could be something about their sex or their height or the BMI or something like that. And then the other key variable is which group are you in, which is on another level. It's not within the school, it's over both schools. You're either in one group or the other, okay? So there's a group level variable, okay? So how do you do this? Well, so one thing you have to consider doing is you have to say, well, what's the data layout? And that's not that easy to figure out either, because think about it, you have 10 students times 3 measurements in each school. So you got 30 measurements in each school, right? And you got 16 schools. So it's 30 times 16, which is, what do I say? 30 times, did I say that right? 30 times 16 is 480. Is that right? So it's 160 times 3, 320, 480. So you got 480 total measurements, okay? And one way to look at it is that, well, each student has got 3 measurements. So maybe the student is the cluster. Each student has 3, so you got students. But then each student is, each of 10 students come from the same school. So if you're worried about the fact that they come from the same school and that's something that makes the outcome on all the students within the same school in some way correlated, then maybe the cluster shouldn't be the student, it should be the school, right? So should the cluster be the student or should it be the school? Should the cluster be the group? Probably not, because it doesn't probably make sense to say everybody in the same group are correlated, because there are different schools and all of that. So, but there is some issue about what the cluster is in any case. But this is the data layout, and that's what the data looks like. Each school, I've got 8 schools, I've got 3 observations on each subject, and this is the 10 subjects within school 1, these are the 10 subjects within school 8, and so on. That's the data layout. Okay, so let's see how we might set this thing up, okay, in terms of doing the analysis. We got 16 schools. I said J is 16 schools. We've got 10 pupils in each school. We've got 3 observations of the outcome on each student. 2 groups of schools. 1 group gets the exposure, and then the dependent variable is FV, the number of fruits and vegetables. So how do we split this thing up in terms of a multi-level analysis? Well, there's a number of ways to do it, but the way I'm going to describe here is we have 3 levels. We have a time level predictor because there were 3 times, so there's measurements at 3 different times. So we got 3 outcomes at 3 different times. And then there's a measurement, a pupil level, maybe what the race of the student is, or what their age is, or what their SES level, or something like that. Then a school level predictor might be what group they're in. That's a school level predictor. Okay. So if we do this and we want to set the thing up in terms of these 3 levels, we'd have to have 3 different models. So here's level 1, here's level 2, and here's level 3. And this is not necessarily the way you'd have to do it. But level 1 is now, I'm considering the time level. And since we're talking about a Poisson regression model, we're modeling the log rate, the log of the count, where the log count has got an offset. The log rate is just linear, and so at the time level, we've got this model. Why have I written the model this way? What do these T's stand for? There's 3 times for each kid, so there's 2 dummy variables for the 3 times. Okay, so that's the model at the first level. And at the model at the second level, now I didn't mention any particular student variables, even though there could be. So if I wanted to add a student variable in there, I could add it to this, but right now I've written the model at the second level. Now I've written the model at the third level, which is the school level. This is the student level, this is the school level, and the only school level variable I have to put in the model is the group level, where they got the experimental control. Now, one thing you notice about what I've done here is you notice I put U0IS, but I didn't put a U0, let's see, U0IS. What did I leave out here? This would be U1IS. And this would be U2IS, right? I didn't put in 2 U's over here. I didn't put 2 V's over here. Now, if I did, the model's going to be more complicated. If I do this, I get a certain model when I concatenate the models together, when I put them together. So depending on what I put in to the second and the third level models, when I group the models, when I put the models together to get a single model, I'm going to get a certain model that involves these terms, but it might be much more complicated if I added some more error terms to the different levels at each of these different levels. The different for each of these different parameters at each of these different levels. So what happens when I do this? Well, what happens when I do this? Combine everything together. I start off with this model, and then I replace B0 beta 0JS with what happens at the second level. This is the first level. I replace what happens at the second level, and then I replace what happens at the third level, and this is what I wind up getting. This is what I wind up getting when I do this. Okay. Now, again, if I had added other U's and other V's, the model wouldn't be as simple as this. Now, what is this model saying? What is this model saying? You tell me what the model's saying. See, it's got U0IS and V0S. U0IS denotes a random intercept for the ith subject within the S school. See, IS, the ith subject within the S school? That makes sense. The ith subject, the ith student within the S school. And V0S denotes the random intercept for the S school. There's only got an S there. So there's a random intercept for the S school. The schools are also could be considered to be a random effect in some sense. So what does this say in terms of, if I saw this and I wanted to write the code for this, what would I do for the code? How would I write the code? I'd have to, the model I'd use would have to be GLIMMIX, right? And the GLIMMIX, because it has to be GLIMMIX because we see there's random effects, we also know it has to be GLIMMIX because we know we're modeling a rate. So it would have to be a GLIMMIX model. So we'd have to write a model statement which has the rate or the count, number of fruits and vegetables eaten. It'd be a count, and there would be an offset. And then what we'd have to do is we'd have to consider random statements to consider whether we want to have what the R matrix might be and what the G matrix might be. So what do we have to do? Look at this. Look at the bottom of the screen. How this is just the putting the data in. The data name of the data set is Gimme 5. It's got the names of the variables and how they're defined and all of that. But here the model. Model is expos is the variable that indicates whether you're in the experimental group or the control group. It's a 0, 1 variable. Okay. Time 2 is a variable that's you notice there's a class variable that says time 2. So time 2 is a class variable that's defined as 2 dummy variables for the 3 times. And then it's got expos times time 2. So what is expos time 2? Expos is a binary variable, right? It's got 2 categories. And expose times time 2 is going to be 2 product terms. Expose times 1 time and exposure variable times the other time. And then I said link equal log, distribution equal Poisson. So this tells me, or tells the computer, that we're doing Poisson regression. If I wrote link equal log and left off distribution equal Poisson, that would also tell the computer to do Poisson, because that's the default thing. If you say link equal log, the program knows to use Poisson. If you said link equal logit, what would the program do? Logistic. So, you know, but if you want to be certain, just write link equal log, because that's, you're doing a log rate to get the Poisson model, and the distribution is Poisson. Okay. Now put this in NL options. This is in order to, it's an optimization technique used in Approximations. It's better than the default because it allows you to deal with some complications with the computer and sort of in trying to fit the model. And then I wrote random residual, random intercept, subject equals school, and then random intercept, subject equals student within school. Why did I do this? Why random residual? What does that do? That's the R matrix, right? What's the R matrix? Independent, because I didn't say type, right? Random intercept, subject equals school. What am I talking about here? Which of the terms am I talking about? U0IS or V0S? I'm talking about V0S, because I'm just talking about the random intercept for a subject within a school, okay? And now I've got student within school, okay? And that's the UI0, what is it? U0IS, okay? So that's, so I've got both random intercepts in there as 2 separate statements, and the, so there's R matrix and there's a G matrix somehow dealing with these 2 random intercepts. So if I run this model, I'm going to get something. I'm going to get an output. Okay, if I run this model, now, again, I want to say that if I had decided from the get-go here to add some U's, I'd have a more complicated model. And that's something you have to decide if you're doing multi-level. Now, most of you aren't doing a multi-level now, so you're not going to worry about this. Okay, but if you're doing multi-level, that's one of the key issues, how you decide to do the 2nd and 3rd level models, or even the 1st model. Okay, but if it turns out I wrote subject, if I wrote subject equal, you see subject equals student within school, if I just wrote out subject equals student, I'd still get identical results. So, but it does make sense to say student within school, because if I wrote the model this way, you can see U0IS is subject within school. So it does make sense to write it that way, even though writing subject equals student, you know, turns out it works, okay? And again, I also use an empirical option, which I didn't put in here. So you run this model, okay? What do you get? Here's what you get. And the main results at the bottom of the screen. I'm running this model, okay? So, and at this point, I'm not testing anything for this model, but that's something you guys might want to do using COVTEST and stuff. So I'm just assuming that this model is the model that I'm going to run. I'm just showing you the output. What do you get out of this? What do you do? Now that you see the results, bottom of the screen, and you notice they're F-tests. Why are they F-tests? Why are they F-tests? Because you're using GLIMMIX, and GLIMMIX does this pseudo-likelihood thing which transforms something so that you can use mixed, and mixed gives you F-tests. So you're not getting chi-square tests. Okay? So if you look at this, what's the first thing you're going to look at in this table, the one that's in the rectangle? What are you going to look at? The interaction, right? This is the interaction. Is there an interaction between the exposure and when they got it? Time. That's what this exposure with time. And the answer is no, right? So what would you probably want to do at this point once you saw this? You probably want to drop the interaction term and run it again, just like we did when we were doing Epi 740. Okay? So I'm not doing it. I'm just telling you how you might proceed from this point. But this is how you might start off. You'd start off with this model, Well, I don't have any other student variables or I mean, student variables or other group variables to put in the model, but if you had other ones, like you guys have, I remember reading what you said, you had other variables in there, and you put them in there, it's going to be a more complicated model, and then you have to worry about interaction and confounding and whatever the, collinearity and all sorts of stuff that I'm not really worried about here. But you'd come up with the best model. The goal of the thing is, suppose you were able to, as makes sense, you drop the interaction, and suppose that when you drop the interaction, what you get for expos and time too didn't really meaningfully change. Let's say it didn't meaningfully change. What would you then conclude based on that? What's the question? What's the question? Do kids getting the intervention, are they doing significantly more the fruits and vegetables than kids getting the regular, the control group? And the answer would be no, right? And if you wanted to come up with an estimate of the effect, again, you'd have to actually run, this model wouldn't do it because you'd have to drop the product terms. But if you want to get an estimate, you have to run the model that doesn't have the interaction terms, and you'd look at e to the beta, where beta is the coefficient of the expo variable, or the expos variable, and that would give you what? What would that give you? It would give you the rate ratio for the effect of whether you're in the experimental group or the control group, controlling for the other variables you put in the model. That's what it'll be doing, which is what you want to get. And you can get a confidence interval for it and so on. So it's the same idea. The only difference between what we're doing now is we have multi-levels, and we're using a model that deals with correlation structure because of the multi-levels. So that's what this model does, okay? So, okay, so you got any questions about that? So again, all I've done to do this is to say, look, if I've got a multi-level situation, I write the models at different levels. Particularly what I do at the second and third levels may make a big difference in what I wind up doing for my code, but granted, that's an issue, and it depends, and nothing much you can do about it other than try different things. So if you guys are going to try different things, that's what you might want to do, try different alternative ways to write the different models and see how it makes a difference on difference in the conclusion. And that's what you do. Now, one thing I did was I said, I was talking about when either of the following set of random statements were used, I got the same answers. And that's just to say that it's not, this is the school and this is the school and the student within school, but all of these things gave us the same, even student time school. So that's another thing to consider. But why that works, I don't think SAS has been very clear on the difference between that. If you tried to read through, so it would be good for somebody when they're doing, if they're doing a multi-level thing, to read through what SAS says and to really see if they can pin that down better. I've never been able to figure out exactly what they're saying about that. This is something, one of the things I might do at some point, but I haven't done it. Okay. So now the only other thing I've done about this example is I've run GLIMMIX and I've also run HLM, hierarchical linear model, to see if how close the answers are, and without going through this output. Bottom line is that the two outputs are essentially identical. Okay, I'm just trying to say that there is another program, you could use another program, and they're essentially doing the same things. When you use the other program, you just tell the computer what the different models are. You see HLM, in this case, I'm writing a level 3 model, and I'm just telling the computer what the 3 models are. And then the computer's doing this, the program's doing this. I'm not doing this thing, just doing 3 separate statements for what the model is. So, but anyhow, just to give you that illustration. So, now, this is the last example I want to do before I quit today, and which means before you quit today. Okay? Now, this is an example that was in the last couple of years. Kristen Wall, how many of you know Kristen Wall? Kristen Wall is one of our faculty, and she's relatively new. She's been on the faculty for 2 years, and 3 years ago she finished her dissertation. And in our department, PhD, and of course she was in this class, because it's required for PhD students. And this was her project. This related to her project in the course, and then it also turns out that she used this as her dissertation topic and expanded things a lot more. So this is another multi-level modeling example. It has to do with topic, which here's the authors. I'm one of the authors. Promotion of couples voluntary HIV counseling and testing in Lusaka, Zambia by influenced network leaders and agents. That's the name of the program. So what's going on here? Okay. The main thing is you've got this area where there's a lot of people have HIV in Zambia. Okay. And there's a group, Susan Allen is the one who has this big clinic, and what they're trying to do is get people to go for testing to see if they have HIV. There's a lot of people have HIV, but a lot of people may be doing things to maybe get HIV, risky behaviors, and don't go to get testing, so they don't even know. So the key issue here in this study was to try to do something to get people to do to get tested. And this was a project to try to get couples that somehow it was determined that they were couples in some way, they weren't necessarily married, and to have them voluntarily go for counseling and testing. So the outcome is whether or not a couple that was identified for the study went for a test or not, whether they got a test or not. That's the outcome, 0-1 outcome, okay? And it was, again, an evidence-based strategy to decrease HIV transmission in the sense that if more couples went to get tested, and just the fact that they're being told that this is something to worry about, they may do better in terms of transmission, and sexual partners are HIV tested together, and they mutually disclose their HIV results. So it's a couples voluntary HIV, couples voluntary counseling and testing thing. And in this process, there were 3 levels. There were 3 levels. Well, first of all, there was the individual couple. There was a measurement at the couple level, at the individual level. It was really the individual couple level. So you had information on a couple and their characteristics. Then the couple was determined from recruiters. I mean, recruiters were identified to try to get couples to go and to be involved in this study. Okay, so recruiters went out, and there was to do that. So there were a certain number of recruiters, and so the recruiters had their own characteristics. Okay, and then the recruiters came from a larger group of what are called network leaders that identified who the recruiters should be. So these network leaders, which are called INL, network leaders, I guess, influential network leaders, they themselves had their own characteristics. So there's 3 levels of characteristics: INLs, recruiter levels, and couples levels. Okay, that's the idea, 3 levels. Okay, the objective is to identify exposures associated with uptake of CVCT invitations in Lusaka, Zambia. And the CVCT invitation meant invitation to go get tested. That was the idea. And the outcome was whether or not they went and got tested. And the question is, what are the predictors that help them determine whether they get tested or not? Okay, and the predictors are measured at 3 levels. That's the idea. Okay, so it's a 3-level structure. Okay, INLs identified recruiters who promoted CVCT in the community to couples for 18 months. That happened over 18 months. It's a 3-level data structure. Groups at different levels may be of different sizes. The outcome measured at the lowest level, invited couples get HIV tested, yes or no, that's the outcome. And the exposures were measured at all 3 levels. So that's the idea. This is a multi-level thing, okay? So now, the number of influential network leaders was K. That's the K, there were K, this is just some notation. There were K influential network leaders. There were M sub K influential network agents or recruiters within the Kth INL. So in other words, if you were a network leader, then you recruited a certain number of recruiters. And the number of recruiters the Kth leader recruited was M sub K. The kth leader recruited M sub k recruiters. The KINL recruited M sub k recruiters. And then the recruiters, they recruited couples. So there are couples within recruiters within INLs. Okay, that's the way it's set up. The dependent variable is whether the couples testing, whether they actually went for, not whether the test was positive or not, was whether they went and got a test or not, whether they agreed to do the test. Because it was trying to get people to go get tested. And again, there are 3 levels of predictors. I mean, at the couple level, one example was cohabitation, whether or not they live together. Yes or no. That was one predictor. At the recruiter level, whether the recruiter was married or not. I'm just giving you an example. And at the INL level, it might have been the marital status, or it might have been, their gender, whether they were male or female. Okay. So that's at the variables at the 3 levels. So we have these 3 levels, and basically at each of the levels, we have variables at each of these levels. And we are interested in the association of these variables with the outcome, whether the couple got tested. But we have to take into account these 3 levels. So that's the idea. Okay. So here's a model that was used. One of several models that was used. Okay. Here's the model at the first level with one variable for the couple level, which in this case, I guess, if we think about what I said, could be any one of those variables. It might be whether they were cohabited. It could be anything. It could be cohabitation status. Let's say it's cohabitation status. Let's say that's the only variable in the model. Now, this is a logistic regression model. This is a logit link, right? So this is at the first level. Now, at the second level, we've got a recruiter variable. The recruiter variable could be any one of a number of variables. It could be age, gender, marital status, and I'm only putting one of them in there. But there may be several Z's, okay? And for each of these, and you notice that where these come from is at the couple level, there is an intercept and a slope. So in order to get the next level model, you have to take a model for the intercept and the slope. If there was more than one x in here other than just a single x, you'd have more betas in the second level model because you'd have to have a slope for any of the x's and in terms of recruiter level variables. And then you'd have as many recruiter level variables. And what Kristen did, at least as a starting point, she started off with an error term for each of the betas that she put in this model. And she had more, but I'm just giving you an example with 2 of them. And then at the third level, we had this INL at the leader level. And one variable that certainly was in there was, I think, was whether the person, whether they either cohabitated or whether they were married or not, or whether they were male or female. I'm not sure what it was. But I'm only putting in one of these variables. There were conceivably several. And you notice there, for each of these different parameters at the third level, there were error terms, okay? So now I've started with these three levels. What happens when I put them together? What happens when I put them together and jointly get them? What is the model that I get? Well, when I put them together, you know, it's a mess. So you get all this stuff, and this is what I wound up with at the bottom of the screen. This is what I wind up with at the bottom of the screen. Okay? And, I mean, I'm putting the random factors in colors so you can see the random factors here at least. And you notice that there's a random intercept at the kth is the INL level, and there's a random intercept for the recruiter within the INL level too. And there's 2 random slopes here for X. There's a random slope for Z, and there's a random slope for the ZX, but there aren't any other random factors in here. So that's the model you wind up with. Okay. Now, and that's the model you wind up with when you start out this way. Okay. It's got everything in there that was in there when you start putting things together here. So if that's your model, what do? Well, this basically says I got random effects in this model, and it's a logistic model, so I have to use GLIMMIX. I'm going to use GLIMMIX. What should my code be? Okay. Well, first of all, again, I've written this model again. This model contains 2 random intercepts, 2 random slopes for x, just like I said, 1 random slope for z, and 1 random slope for the product. I already said that, but that's just summarizing that again. So what do you do next? What you do next is you write the code for this. Okay? This tells you what the code should be. This is where you got to look at the model and look at what the code is. Okay? Now, notice I've got proc GLIMMIX. The data is the Zambia data. Again, I've got RSPL because that's the one most people use. I've got the model that has x, z, g, x times z, x times g, z times g, x times z times g, because those are the variables in the model. Those are the fixed effects in the model. So that's in the model statement, right? It says link equal logit, distribution of, I could leave out distribution equal binomial, or I could leave out link equal logit, either one. I've got this optimization thing just to make sure the computer deals with some problems that might have fitting the model. Then I've got random residual, which means I'm using an R matrix that's independent, but I'm basically basing most of the correlation structure on the random variables, the random effects that I'm putting in. So one random effect I'm putting in is random intercept, it says random intercept xz, x times z. And then it says subject equal INL. What does this refer to? What does this refer to? Intercept xz, x times z. Okay. Now, if you look at this thing, there are some v's and there are some u's in there, right? The v's have to do with what? The INL. If we go back to the original way things were coded, the v's have to do with INL, and the u's have to do with the recruiter, right? So, just going back to this thing, by saying subject equal INL, and you notice there are 4 V's here, right? 4 V's, okay? So, and there's 4 random terms I'm putting in here. So these 4 random terms are corresponding to those 4 V's, okay? And then you notice that there are 2 U's, right? And this is random intercept X subject equal INA within INL, because this is the recruiters that were in INLs, were in natural, in the leaders, okay? And I could have written it as INA times INL, but this is the model, okay? So corresponding to this, I get this model. That's sort of how you do multi-level, but now the next question is you run the model, okay? Okay, I ran the model. Let's see what happens. I'm just illustrating it again, but it's model A. Won't run. Model doesn't run. Doesn't meet our a priori assumptions. No interaction terms of interest. No INL level exposures. Too distal to affect the outcome. So basically, Kristen said, this won't work. I got to improvise. Got to do another model. That's what you're going to have to deal with for your project. You might have to deal with, whether you're doing multi-level or not. So here's a second model. Okay. Here's a second model. This is model B. Okay. What's the difference between model B and model A? Well, model B got rid of this variable for the slope in the second model and got rid of the G variables, all the INL variables, got rid of those variables. It didn't use any of the INL predictors as variables as predictors in the model. Now, why she did that is because, you notice I said, no INL level exposures, too distal to affect the outcome. That's why she dropped those. She dropped the G or anything that was like a G because she felt like using an INL variable was not going to relate to whether the couple went and got tested or not. So she dropped that. Okay, she ran this model. Okay, so I've got model B now. And if you're running model B, the code changes. The code changes. It's now intercept X and for a recruiter within INL and random intercept XZ. So it's a different, maybe I've got it. This is XZ, X times Z, subject equal INL. This is the code originally, and now the code changes. Okay? So it's an attempt to try to get a model that runs and that considers what made sense in terms of what variables you might drop. She ran that. Okay. Not positive definite. Okay. what's going to happen? You know, this is when you start saying, maybe I shouldn't be in this class. I'm not sure, you know. Enter Model C, no random slopes. Here's Model C, okay? Model C it got rid of the Z and the U. I guess the other one got rid of the Z, but didn't get rid of this U. This was a random slope. Got rid of all the random slopes, and it only kept this U and this V in the model, and everything else, the G's were dropped, this Z and this U were dropped. So that's Model C. And when she ran Model C, she winds up getting just these two terms. This is so similar to what happened with the Gimme 5. The only two terms in the model were the random intercepts, or terms that contributed to the intercept. And so this would be the code. You see, it says random intercept, subject equal recruiter with an INL, and random intercept, subject equal INL. That's the model that follows from this thing, because there's no random slopes in this model at all. So that's how you'd code it. You'd run the model, and you'd see what you'd get. Again, the question of interest is, what are some of the predictive variables that are being put in the model, and to what extent did they illustrate that they were important predictors of whether somebody went testing, did testing or not. So again, there were certain issues about what turned out to be equivalent. I'm not going to talk, but this is the empirical and model-based. So she ran GLIMMIX, she ran it for model-based, was assumed that the correlation structure was the correct one, whatever the G matrices were correct, or that they weren't, empirical. And she wound up getting, this is an example of the output for empirical versus model-based. Now you notice that one of the variables, one of the recruiter variables was network, okay? And there's one of the categories of network turns out to be significant. So it looks like where the recruiter, what network the computer came from, whether they were in a private network, a religious network, I'm not sure what that meant, health management, or whatever the network was, seemed to be possibly a strong predictor or a significant exposure. Age and whether or not the recruiter read English or not were not significant. I mean, this is just to give you an example of what happened. And you get the same conclusion whether it's empirical or model-based. And then what she also did was she did some COVTEST stuff. I'm only going to show you one just to show you how it worked, and then we're done. Okay? She did you here's the COVTEST. Okay? This is where she did GLM. Okay? She did GLM. Now GLM is doing what? What's GLM doing in this case? Let's see if I got it. Here's what she did. This is the model, random intercept, random intercept. This is exactly the model, but now I've added two COVTEST statements, two COVTEST. One is no G side effects, 0 G, and then I've written independent GLM. Okay. Now, what the model is? What's the model? The model is R is independent, and the G matrix is a 1-by-1 matrix, and it's composed of a scalar that has to do with the sum of the two random effects that go into the intercept. That's what the G matrix is. And when you wind up running this thing, when you wind up running the COVTEST, either one of these is testing the same thing. Because if you do the 0 G thing, you're basically saying there's no random effects. If there's no random effects, the reduced model is independent, right? If you do the independent, you're also saying there's no random effects because the R matrix is independent. So these two will give you the same answer, and the same answer was this. Okay? This says we need to retain some of the G effects. Okay? So I'm just showing you one use of the COVTEST thing in this case. Now, it doesn't say whether you need to retain one of these and not the other, which is something you can do using those zero dot statements. So there are some things you can do even to go further with this. But all I'm saying here is that maybe this is it. This had to do with testing for significance of some of the but she used walled statistics to do this. And so a summary of our results were they found that after all was said and done, using Model C, they found a certain number of recruiter level statistics characteristics seemed to be important, and a certain number of couple level characteristics. What I showed you in this slide over here was just an example to illustrate some of the outcomes. some of the results, but this was her conclusions from the whole thing, after she did this whole thing and considered all the possible models and that she had to do. So this is a second example of multi-level, and the key idea is multi-level is just a way of putting several different variables at different levels in the same model, and the way it's usually done is you do models one level at a time, you combine them based on their combination, you determine what the code should be when you're running GLIMMIX. You run the thing. If the model doesn't run, you improvise and run a model that keeps changing things until you get a model that runs. That's it. So do you think you understand what, the only way you're really going to understand doing it, like you guys who are doing it, is to do it, right? And for those of you that don't have a multi-level problem, you're never going to know until you have an example to do that, okay? So we're done, and it's 10 after 5, so we're done. Are we done? You have any questions about multi-level? You're welcome to ask questions. This is a hard class to ask questions in, isn't it? I think it's a hard class to ask, because it's complicated. Sometimes you don't know what to ask, but you can ask. That's okay. I don't mind trying to answer anything. Kevin? You're going like this. No questions. Jake? No questions. Okay? And when you have no questions, I'm not sure what that means. Total obscurity or total understanding or whatever. Anyhow, that's fine. We're done. So, next week.